This is part 3 of section 3.2. We want to use transformations of the graph of log base 2 of x, which we just graphed in the previous part, to sketch the graph of y equal to negative log base 2 of x minus 3. Our transformations work the same way as they always have. If you have a negative in front, that is going to be a reflection over the x-axis. Okay, and then here we have an x minus 3, and this is inside of our logarithm. So this is going to be a horizontal shift. And since this is a minus sign, this is going to the right 3. Okay, so one of the first things you want to do is your asymptotes shift along with the rest of your graph. And a logarithm in general has the y-axis as an asymptote, so this is going to move right 3 as well. So let's go ahead and draw that in. Okay. And now I'm just going to take the points that we developed in the previous part, and these values are right here. Okay, and then I will graph these, and I'll take these values, which are our original, and shift them all. Okay, so if I had the point, I'm gonna do this right here. I'm gonna start with 1, 0. 1, 0 is right here. And I would flip, and I'm going to move it to the right 3. And then I would shift it over the x-axis, but there's nothing to shift. So that's right there. Okay. Now if I do 2, 1, that's right here. I'm going to move it right 3, but then I need to flip it over the x-axis, so that's 1 up here, so I'm going to go 1 below here. 4, 2 would start off here, go right 3. So 2 units away up here, I move it 2 units away on the bottom. 8, 3, if I move it right 3. And then, so I'm 3 units away up here, so I go 3 units away here to get that point. And now let's quickly do these. If I had been at 1/2 and I move it 3 over, I'm about right here. I'm halfway between here and here. And I was at -1, now I move it to the other side. And you can see that this is going to get closer and closer that way. So this graph, once we have taken care of all of our transformations, is going to look like this. Okay. Now we're going to talk about 2 special forms of logarithms. Because our world uses a base 10 system, we end up with a lot of exponentials in the form 10 to a power. So it is common that we need to take a logarithm of base 10 once we do transformations back and forth. It happens so often that we drop the base 10 off of it. So if you see log base nothing, that is an understood 10 right there. Okay? And if you have trouble remembering this, your calculators will help you. They usually either share a button or there is a pattern to it, okay? So for this calculator, you see 10 here, and that's the second thing listed here, logarithm 10x. And then here, regular log and 10 to the x. So they share a button here. So your calculator can help you remember. Okay, so let's do an example problem here. Benford's law states that the chances of the digit m occurring as the first decimal digit from 1 to 9 for many real-life data sources is given by this. P sub m is equal to log, that's common log, of m plus 1 minus log of m. Okay? That means that 100 times the value you get right here, that's going to change it into a percentage, of the data can be expected to have m as the first digit. This law is important. A lot of auditors use it to try to locate falsified information on tax returns and things like that. Okay? So what we're going to do here is we're asked to find p sub 2 and then interpret the results. So I'm going to take the 2 and it's being plugged in for m here. So p sub 2 would equal common log of 2 plus 1 minus common log of 2. Okay. If you go to your calculators and you punch this in, you will get that this is approximately equal to 0.17609. And then they want us to find out what percentage of the, we found P2. Now interpret the result. We need to know what percent, so multiply this by 100. And you'll get 17.6% about of the data should have 2 as a first digit. Okay. And now, natural logarithm. Okay. The logarithm with base e, and we talked about e in the last section, is the Euler number, Euler constant. It is called the natural logarithm and is denoted by lnx. Remember, this is an L, it is not a 1. And it is an understood base e. Why ln instead of nl? It's because the person who named it in Latin, not in English. All right, and again, just like the 10 to the power, if you look here, your ln and your e to the x are in the same position here. And on your graphing calculators, natural log and e to the x share a button as well. Okay, so let's just look at some example problems here. We want to evaluate this. Natural log of 1 over e. Well, this is the same thing as natural log of e to the negative 1. Now, you may not need to write down this step, but this is the same thing as log base e of e to the negative 1. One of our basic properties was if you have the same base here and here, then your answer is your exponent. So this should be simply negative 1. Okay, now let's find natural log of 2. In this case, we are going to have to go to a calculator and get a decimal approximation. Okay, so if I want to find natural log of 2, that is my answer. So this is approximately 0.69315. And now let's look at continuously compounding interest. We dealt with this form of the formula in the last section. And we also have the same formula written in logarithmic form. All we've done here is we've solved this so that we have r and t on the same side. Often we will be asked not to find the amount we have at the end, but what should the rate be, or what is the time? And this form of the equation will be easier for us. So let's look at this problem. How long would it take you to triple your money if it earns 6.5% compounded continuously? So continuously is important so that I know to use these formulas. This is going to be my rate. And what I don't know, and actually it doesn't matter, I don't know what my initial value is. My principal is my principal. And I want to know how long it takes me to triple this. So my A value is 3 times my principal. Right? We want to know how long it would take, so I'm looking for T. So let's plug all of this into this formula here. Natural log of A, which is 3p, divided by p, is equal to my rate as a decimal, 0.065, times time, which is what we're looking for. Okay. Those cancel out. So what we have here is natural log of 3. And if I want just t, I can divide this by 0.065. And that's going to give me my t value. If you plug this into your calculator, you'll find that t is approximately 16.9. So you can triple your money in about 17 years. And it does not matter how much money your initial deposit is. It's still going to take the same amount of time to triple your money. Okay, now let's reverse this. Essentially, where we have the amount of time, but we are looking for the rate. We are still looking to triple it, and we're still compounded continuously. So for part B, I will have natural log of 3p over p equal to 5 times r. So I have natural log of 3 divided by 5, and that's going to give me my r value. Plug this in, and you'll find that r is approximately 0.21972. So the rate that they will want your answer as a percent, so multiply this by 100. You'll need a 21.972% rate to triple your money in 5 years.